In this lesson, we're going to be looking at graphing various equations. We will also look at the idea of finding intercepts and also determining symmetry of equations. These will be tools that will help us to make graphing a little bit easier as we go along. Now, this is an introductory lesson on graphing. You're going to find as you go through and you learn more about equations, there will be some things you can look for that will help you to do graphs much easier. In this lesson, we're just going to start with the basics of graphing. The first thing that I want to do is to look at a definition of what we mean by the graph of an equation. The graph of an equation. The graph of an equation in x and y is the set of all points x, y in the coordinate plane that satisfy the equation. Notice we're talking about locating some ordered pairs x, y, and we want only those ordered pairs that satisfy the equation. Now, do you recall what it means to say something satisfies the equation? That, of course, means that it makes the equation true, doesn't it? So our first problem here is going to ask us to determine if the given points are on the graph of this given equation. So that means, do these points satisfy the equation? Our equation is y equals the square root of x plus 5. Now, let's take a look at our first ordered pair that's given here. This, of course, means that we're going to let x be 4 and y be 3, and we want to know if that makes this equation true. So to do that, let's just simply substitute 3 for y. So I'll put a 3 here. Now I'm going to put a question mark on this equal because we're not sure yet whether this is equal or not, but we will determine that. We have a square root sign. In place of x, we're going to put 4 plus 5. And now we'll simplify, and of course it becomes pretty obvious that this is going to be true. 4 plus 5 is 9. Is 3 equal to the square root of 9? Well, of course, yes it is. So this point, 4, 3, is on the graph of the equation. So yes, it's on the graph. Now, let's look at our second point. For our second point, x is -1 and y is 2. So again, let's substitute in. If y is 2, we want to know, does that equal the square root of -1 for x plus 5? Again, as we simplify, we can see that -1 plus 5 is 4. Is 2 the square root of 4? Yes, it is. So this second point also is on the graph. Now, let's go to our third point where x is -21 and y is 4. Put 4 for y. Does that equal the square root of -21 plus 5? Now, as we simplify here, what's going to happen under this radical? -21 plus 5 is going to be a -16, isn't it? What do we know about square roots of negative numbers? Those are not real numbers, are they? That's a complex number. It involves the imaginary number I, if you recall from previous studies of mathematics. In this situation, remember, we're talking about the graph containing ordered pairs in the coordinate plane. Now, when we talk about points in the coordinate plane, our ordered pairs must contain real numbers. So since this is not real, the square root of -16 is not real, it does not equal 4, this point is not on the graph. In fact, we cannot even use -21 to substitute into this equation. So this one is not. Okay, our last point here, y is -4. So let's put that in, -4. Does that equal square root of, x is 11, 11 plus 5. So we have -4. Does that equal the square root of 16? Now, what about the square root of 16? All of you know that if you square -4, you can get 16, can't you? But I want you to understand what this symbol means when we write it in an equation. When you see this equation, y equals the square root of x plus 5, this square root symbol here means the principal square root. Now, the principal square root is the positive square root. The only way that we could be looking for the negative square root here would be if we had a negative in front of the square root. When we write that, this is asking for the negative square root. Now, were we looking for the negative square root? No, we were not. So even though we can square negative 4 and get 16, negative 4 is not the principal square root, which our equation is asking for. So this is going to be not on the graph because of our symbol for the square root sign there. Now, I wanted to review a couple of concepts with you with that particular example. One being that when we're working with graphing these equations, we're going to be working with real numbers, so we have to watch for not having negatives under that radical sign if we have a radical in our equation. And the other concept was that if we see that square root and there's no sign in front of it, then we're looking only for the principal square root. Now, having just looked at a problem here where we determined is a point on the graph of the equation or not, we're going to turn our attention to doing some graphing. Now, at this point, we've not learned anything special about these equations, so what we're going to do is a technique that we refer to as plotting points. That means by trial and error, we're going to find some points that are going to be on the graph of this equation. We'll just be selecting points, values of x at random or whatever. And then once we have found enough points that it becomes clear to us what the graph is going to do, then we will complete the graph of the equation. Let's take a look at one. Sketch the graph of the equation by plotting points. Our equation is 2x minus 3y plus 6 equals 0. Now, I suspect some of you may have seen a problem like this before, and you may already know what's going to happen with this graph, but let's just assume we know nothing about the graph. To make it easier to find values to substitute in here, I'm going to take this equation and solve for y. So I think what I'll do, since all the terms are over here together, I'm going to add 3y to get rid of it on this side, and then that will put it over here as a positive 3y. So let's rewrite. We have 2x plus 6 is equal to a positive 3y. We just added 3y to both sides of our equation. Now, we'll divide everything by 3 to solve for y. So I have 2/3 x plus 6 divided by 3 is a 2 is equal to 1y. Okay, now that's just going to make it easier for us to find some points. Instead of writing these as separate ordered pairs, I'm going to do just a table of values for x and y here. And we're going to choose an x value, substitute in, and find the corresponding y value. That's why I wanted to solve for y, to make this process easier. Now, we're going to make this as easy on us as we can by choosing what I call nice values of x. That means values of x where it will not be difficult to substitute in and find the corresponding y value. One nice value of x here is 0. What happens when you multiply 2/3 times 0? That's 0, isn't it? So if x is 0, this term is a 0. 0 plus 2 gives us y equals 2. So that was easy to do, wasn't it? Since I have that point, I'm going to go ahead and locate it over here on my graph. I have the point 0, 2. Okay. All right, let's choose another easy value of x. I think that might be 3, for instance. Think about when you do 2/3 times 3, and then we've got plus 2 is equal to y. What happens here? These 3's cancel, don't they? So I have 2 plus 2, or y is 4. Okay, let's graph that point 3, 4. 1, 2, 3 for x. 1, 2, 3, 4 for y. Okay? Well, what's another easy value that might work? What I'm looking for, in case you're thinking ahead of me, is a number for x where that 3 is going to cancel with it and give me a whole number. What about if we use x equals 6 here? 2/3 times 6 plus 2 is equal to y. This 3 is going to cancel with the 6 and leave a 2. So I have 2 times 2 is 4, plus 2 is 6. So whenever x is 6, y is also 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, now since we're sort of running out of space here, let's choose a negative value for x. What if we use negative 3 for x? What's going to happen if I put a negative 3 here? The 3's will cancel, but remember you'll leave a negative 1 factor. If you need to write that down to look at it, you have 2/3 times negative 3 plus 2 equals y. When you cancel these, you have a negative 1 factor left. So you have a negative 2 plus 2 is 0. Y is 0. negative 3, 1, 2, 3, y is 0. Do you sort of already get an idea of what's happening with these points? It looks like they're on a perfect straight line, doesn't it? Okay. Now, just to maybe see if this is really going to hold out all the time, I'm going to choose a number that might not be so nice. I'm going to choose x equals 1. Okay? If x is 1, 2/3 times 1 is 2/3. 2/3 plus 2, I can just write as the mixed number 2 and 2/3. Okay? Well, we're going to estimate if x is 1, y is 2 and 2/3. Notice when I estimate where that point is, it's still falling on that same line there, isn't it? So it looks like we've got a definite idea of what this graph is doing. And so I'm going to simply line up those points that we have and connect them. Okay? Now I want to caution you here that when you're just plotting points, you have to plot enough points so that you're absolutely sure you know what your graph is doing. Now as you go through your college algebra course, you're going to learn a lot more about equations, and you'll find out that you'll know just by looking at the equation a lot of times whether your graph will be a line or a circle or some other objects that you will become familiar with. Okay, let's do another equation. We're going to sketch the graph again by plotting points. Now this equation has already been solved for y, so it will make it real easy just to find values of x here and put those in. So let's set up an xy table like we did a while ago. And I'm going to start out the same way we did a while ago. Let me choose x to be 0. This will make that real easy. If these x's are both zeros, these terms are zeros. 0 plus 1 is 1. So whenever x is 0, y is 1. Now, since I don't have any fractions, I'm not going to worry too much about particular values, so I'm just going to go in order here for a minute. Let me let x be 1. Okay, if x is 1, 1 squared is a 1. Let me write that down here so we can keep up with it. If x is a 1 here, negative 4 times 1 is a minus 4. And then I have a plus 1, don't I? So 1 minus 4 is negative 3. Negative 3 plus 1 is a negative 2. So I have the point 1, negative 2. Now let me caution you here. Those points are a line if I line them up, but I don't have enough points here to make that decision that that's exactly what this graph is going to do. The other thing I will tell you is sometimes you can do this arithmetic in your head, do it mentally without writing this down. I just encourage you to write down what you need to write down so that you're getting a correct y value and not making careless mistakes. Okay, well let's go on and choose x to be 2 and see what happens. If x is a 2, 2 squared is a 4. Here, if x is 2, negative 4 times 2 is a negative 8, and then plus 1. Well, let's see, 4 minus 8 is negative 4. Negative 4 plus 1 is a negative 3. Now let's locate that point. 2, 1, 2, 3. Now I want to show you right here. If I line these 2 points up, I'm going to miss that one. Or if I line these 2 up, I'm going to miss that one. That tells me right away this graph is not a line, is it? It's some kind of a curve. So we're going to need some more points before we can determine exactly what this curve is doing. Well, let's go ahead in succession here for a while. Let's choose x to be 3. 3 squared is 9. 3 times negative 4 is a minus 12 plus 1. 9 minus 12 is a negative 3. Negative 3 plus 1 is a negative 2. Okay, so whenever x is 3, y is negative 2. Well, that's interesting, isn't it? Okay. Well, let's keep going and see what else happens. Let's choose x to be 4. 4 squared is 16. 4 times negative 4 is a minus 16. Then you have a plus 1. Well, 16 minus 16 is 0. 0 plus 1 is 1. 1, 2, 3, 4. Did I miscount? 1, 2, 3, 4, 1. There we go. Okay, well, let's keep going. How about 5? 5 squared is 25. 5 times a minus 4 is a minus 20 plus 1. 25 minus 20 is 5 plus 1 is 6. Whenever x is 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Let's choose a negative number for x and see what happens. Let's use a negative 1. Now remember, if you square a negative 1, you get a positive 1, don't you? If you put a negative 1 here, negative 4 times negative 1 is a positive 4. and then plus 1. Well, 1 plus 4 is 5, plus 1 is 6. Negative 1, 1, 2, 3, 4, 5, 6. Now, isn't that interesting? Notice how these y values are sort of repeating themselves here, and it looks like we're getting a nice pattern. Do you see what this is doing? This is sort of a low point right here. This is a curve. It's not a straight line. And I'm just going to kind of gently try to connect these points in a curve. And going this way, I'm going to do the same thing. And then the question is, does this continue just to go up? Well, we might pick a number. Let's see, how far did we go? Well, it went up to x equals 5. Let's do x equals 6, and let's see what happens there. 6 squared is 36, minus 24, plus 1. Well, let's see, 36 minus 24 is 12, plus 1 is 13, isn't it? So whenever x is 6, we are going to keep going up larger, so I'm just going to put an arrow indicating that thing keeps going up. And let's see, let's move over and do a negative 2 and see what happens. If we square negative 2, we get 4. Negative 2 times negative 4 is a plus 8 and plus 1. And look what we're getting here. We're getting another 13, aren't we? So on this side, it also continues to go up. And so our graph looks something like this. Now, you may be realizing just from this example that it took quite a few points here, plotting points. You will learn later in the course how to look at this equation and know that you're going to get a shape, something like this, and then it will not be necessary to do quite so much work here to find out the graph. Okay, I have another equation here. Now you'll notice this one involves an absolute value. Y equals the absolute value of x plus 2. So again, since this is solved for y, let's just go ahead and find some values here and see what happens. Okay, I'll start with 0 again. That seems to work out pretty good. If x is 0, then y is the absolute value of 2, which is 2, isn't it? If x is 1, then 1 plus 2 is a 3. I have the absolute value of 3 is 3. If x is 2, 2 plus 2 is 4. The absolute value of 4 is 4. And if x is 3, 3 plus 2 is 5. Absolute value of 5 is 5. Now that seems to be going along real fine. Let's locate those points. 0, 2, 1, 3, 2, 4, and 3, 5. Now those are in a perfect line, aren't they? Now, a lot of students make a mistake right here. They just connect those points and assume that they have the graph. But you'll notice what we have not considered here is any negative values of x. So we don't want to draw that graph in too soon. Let's pick a negative number for x and see what happens. If x is negative 1, negative 1 plus 2 is a 1, isn't it? The absolute value of 1 is 1. Let's locate that point. I have a negative 1, 1. Well, that's still in a straight line, isn't it? Well, let's try negative 2. What happens at negative 2? Negative 2 plus 2 is 0. The absolute value of 0 is 0. Do you think we've got enough points? Well, let me show you one more, and then I'm going to let you see that you can't be too careful here. Let's let x be negative 3. What happens when you do negative 3 plus 2? Negative 3 plus 2 is a negative 1. What is the absolute value of negative 1? It's positive 1, isn't it? Notice right here at x equals negative 3, I get a point up there. Well, let's keep going a minute. Negative 4. Negative 4 plus 2 is a negative 2. What is the absolute value of negative 2? It's positive 2, isn't it? Negative 4 gives us positive 2. Now, one thing that you could be thinking about, and I hope that you learn to watch for things like this, when I see the absolute value sign here, what does that tell me? That tells me my answer will never be negative, will it? An absolute value of a quantity is never negative. Y can never have a negative value then. So I know that I will never have any points down here where y is negative. So that would tell me if my temptation was to connect these points in a straight line and keep coming down, that could not be right because I would be getting negative values of y down here, and I know that can't happen. You will study these absolute value equations a little bit more thoroughly later, but you'll find that typically they have this V-shaped graph. I'll do that without a ruler, but actually these are a straight line here. These are a straight line here, but they come together at this point and form a V-shape. Okay, I want to do one other equation where we're just sort of plotting points just to explore some differences here. Sketch the graph by plotting points, and we have x squared plus y squared equals 9. Now, we've been trying to get this equation solved for y to make it easier to find values to put in here. So let's do that with this one. Y squared, I'm going to subtract the x squared, is minus x squared plus 9. Now, to solve for y, I'm going to need to take a square root. Now, I want to talk about this to point out a difference. Earlier, we had a problem that said determine if the points are on the graph. You remember that one? And we were given the equation y equals the square root of x plus 5. I want you to notice this was the original equation. The square root sign was already there. And that's when we talked about then that meant the principal square root. Here, the situation is a little bit different. I have y squared and I'm wanting to find y. So I'm going to introduce a square root sign, but I have to consider that if I have y squared here, there's nothing that says y can't be negative, is there? So when I take the square root, I'm going to have to consider I could take either the positive or the negative square root. And I'm going to change this around just because of that negative and write that as 9 minus x squared here. Okay? So I need to consider when I put a value in for x right here, I'm going to get two answers for y. Okay? Because I can get the positive or the negative answer. Okay, let's do a table. And since it's been working quite well to choose x to be 0 to get started, I think I'll do that. If x is a 0, 9 subtract 0 is 9. The square root of 9 is 3, isn't it? So notice this is plus or minus 3. I'm going to write it like that over here, plus or minus 3. Notice that gives me 2 points. If x is 0, y can be positive 3 up here. Or if x is 0, y can be negative 3. So I have 2 points already. Okay, well let's see. Let's choose x to be 1. If x is 1, 1 squared is 1, 9 minus 1 is 8. So I have plus or minus the square root of 8. Now, you can simplify the square root of 8 if you recall. If you want to do that, if you write 8 as 4 times 2, you can simplify that to 2 times the square root of 2. Now, if it's been a while since you've done that, we do have videotapes on simplifying square roots, and you might want to check that tape out to get some help with that. I wanted to write it like this just to get an approximate value since I don't have a calculator handy. I know that the square root of 2 is about 1.4. Now, that's just an approximate value. 2 times 1.4 would be about 2.8. So that will give me an approximate location for this point. Notice again that's plus or minus. So whenever x is 1, my y value is approximately 2.8. It's not quite up there to 3, or perhaps it's negative 2.8. Okay? So you see those points right there? Okay. Now while we're here, I want to do this. I'm going to go ahead and choose x to be negative 1 because I want to point out something here. Be real careful with this. A lot of students get confused right here. The square happens before the subtract happens. Remember that order of operations? So if I'm putting a negative 1, I'm going to square the negative 1 and get 1. And then that means I'm going to subtract 1 from 9, and I'm going to get 8 again. Do you see that? So if I choose x to be negative 1, I'm going to get exactly the same answer that I got when I chose x to be positive 1. The reason for that is when I square, it doesn't matter if it's positive or negative, I'm going to get the same answer. And the squaring happens before that subtract happens. That's the important key. So notice if x is negative 1, I'm going to have that same approximate 2.8 or negative 2.8 values right there. Okay? Okay, well let's see. Let's try x being 2. Now 2 squared is a 4, so 9 subtract 4 is 5, plus or minus the square root of 5. Now, I don't know the exact value of the square root of 5, but I do know it's between, 2 and 3. And I know the square root of 5 is going to be smaller than the square root of 8, isn't it? Okay? So, let's see, whenever x is 2, I'm going to get a number larger than 2, but not as large as that answer we had a while ago. And I will have possibly the negative value there. Notice if I choose x to be negative 2, the same sort of thing happens. I'm going to square the negative 2 first and get 4 9 minus 4 is still 5, plus or minus square root 5. So over here at negative 2, I'm going to have those same sort of values here. Okay? Okay, well, things are working out pretty well. Let's try x equals 3. 3 squared is 9. 9 subtract 9 is 0. The square root of 0 is 0. So whenever x is 3, y is 0. And notice if x is negative 3, again, I'm going to square it first and get 9. 9 minus 9 is 0. So negative 3 also gives me 0. Now, does that sort of give you a hint of what this graph is? Actually, it turns out this is the graph of a circle. And again, this was quite a bit of work, and we had to use some approximate values to get that. Later on, in one of the later lessons, you're going to learn more about these circles and how to get the graph much easier than what we've done here. I do want to point out that I cannot use a number larger than 3 for my x value. Notice what happens if you try to use x equals 4 here. You would get a 9 minus 16 under that square root. That's going to be negative, isn't it? That's not real. And so it's not going to be possible to use any x value larger than 3. And as it turns out, I can't use any of these x values over here either, because again, when I square first, I'm going to get a number larger than 9 to subtract from 9, and I'll get a negative under there. So we will not have any values for those other x's there. Now, what we've done so far, as I said, is kind of a trial and error thing where we're just simply trying to find enough values, coordinates of points that work in the equation so that we can get an idea, based on what we see those points doing, what the graph is. And of course, you can see already that sometimes it becomes tedious because you have to find so many points, and also sometimes you're not real sure, when have I found enough points to be certain what this graph is doing. So what we're going to do now is to start you on some things that will help you to streamline your graphing process a little bit so that you don't have to work quite so hard to get these graphs. The first thing that we're going to talk about are intercepts of a graph. Let's look at the definition of intercepts. Intercepts, the points at which a graph intersects either the x or y axis, are called intercepts. To find x-intercepts, let y equal 0 in the equation, and to find y-intercepts, let x equal 0 in the equation. Now, let me put this graph of a circle back up here a second. Where you cross either the x-axis, that would be here and here, or the y-axis, here and here, are called intercepts. So this circle has 4 intercepts, 2 y-intercepts and 2 x-intercepts. Notice anytime a graph is crossing the x-axis, or if a graph is touching the x-axis, that would be considered intercepting it. Your y value is 0 at that point, isn't it? Anytime a graph crosses or touches the y-axis, your x value for that point is 0. So that's the reason that we have the rules here. To find x-intercepts, we know our y is going to be 0, so we'll substitute that in and find the corresponding value of x. And then vice versa. To find y-intercepts, let x equal 0 and find the corresponding value of y. Now you're going to want to think about this and be sure you understand this. It's not difficult, it's just remembering what to do. So our next problem is to find the x and y intercepts. Okay? Now, usually it's easier to find the y-intercept because like when you look at this equation, it's real easy to let x be 0, isn't it? Okay? So I'm going to find the y-intercept first, and I'm going to do that by letting x equal 0, just to remind you what we're going to do. Now, obviously, if x is 0, then y equals -4. Do you see that? If these are zeros, 0 minus 4 is a -4. Now, sometimes people just say the y-intercept is -4. Other times, I like to write the y-intercept as a point because this is a point on the graph. Now, what did we do to get the y-intercept? We let x be 0. So we're saying the y-intercept has an x-coordinate of 0. Whenever the x is 0, the y value is -4. Now, it really sort of depends on your instructor which way they might want you to indicate the y-intercept. Sometimes y equals -4 is sufficient. Sometimes they would rather have the point. I sort of like this form because it reminds you that x is 0 and it reminds you how to locate that y-intercept on your graph. Now, to find the x-intercept, remember, we're going to let y equal 0. So if I let y be 0 in this equation, I have 0 equals x squared minus 3x minus 4. Now, how do you solve an equation like this? It's a quadratic, isn't it? So isn't the idea we have 0 on one side, factor if we can? Let's see about factoring this one. X times x, we know we have opposite signs, so we'll need to use the 4 and the 1. Minus 4 plus 1, check that, make sure I have the correct factors here. You can't get the correct solution if you don't have the correct factors. And again, we do have videotapes on factoring if you need help with factoring. Okay, the next step, of course, is to set each factor equal to 0 and solve for x. So I'm getting x equals 4. And on my second factor, if I set that equal to 0, I get x equals negative 1. I have two solutions. Now again, sometimes this is sufficient to say my x-intercepts are 4 and negative 1. But also, again, I prefer really writing the points. We're saying x is 4. How did we get an x value of 4? By letting y be 0. So I'm going to put a 0 for y. Also, x is negative 1, and that also occurred whenever y was 0. So I know that the graph of this equation right here is going to have these 3 points, and I can go ahead and locate those points. They were easy to find, and I know exactly then where my graph will either cross or touch either of my coordinate axes. Okay, well, let's do our second one. If I'm looking for the y-intercept, remember again, I let x equal 0. So my equation then will say y squared plus 4 equals 0. If x is 0, that's going to be gone. What happens when I solve for y squared? If I subtract 4 from both sides, my equation says y squared equals negative 4. Now remember, if I'm working with real numbers only, can this happen? Can y squared be negative 4? No, it can't. There is no solution here. Okay? Now we were looking for y-intercepts, and when I let x be 0, I got no solution. This tells me there are no y-intercepts. If there are no y-intercepts, then my graph will not touch or cross the y-axis. Okay? So I know my graph absolutely will not touch that y-axis. Now, let's go ahead and check for the x-intercepts by letting y equal 0. If y is a 0, my equation is negative x plus 4 equals 0. If I just add x to both sides, then I get what? 4 equals x. So x is 4 whenever y is 0. That tells me there's only one point where this graph is going to touch or cross either axis. It will only touch or cross the x-axis at the point 4, 0. Intercepts are usually very easy to find, or you can very easily determine that there's not one, like we just saw in that last example. And it really does help you have information about the graph without finding so many other points. We're also going to couple with finding intercepts the concept of symmetry. Now, most people have an idea of what we mean by symmetry, and we're actually going to look at a graph and talk about what that means on the graph, and then we're going to give you some rules that you can follow to test an equation for symmetry. Now, here I've just got a graph, and I've just titled this symmetry, but what I want you to notice on this graph, this half of my graph right here looks exactly like this half over here in terms of it being a mirror image. Now, the mirror, of course, would be what? My y-axis. So we say this graph is symmetric to the y-axis. Okay? Symmetric to the y-axis. That just means two things. The right-hand side is a mirror image of the left-hand side with that y-axis as a dividing point. We would refer to the y-axis as the axis of symmetry. You can also picture, if you were to fold your paper on the y-axis, that the two halves of your graph would coincide. That means one would be right on top of the other. But we can actually picture that symmetry. Now, I want to show you in terms of points on this graph. Notice this point right here and this point right here, which is directly across the y-axis from it. What are the coordinates of this point? 1, 0. I'm sorry, 1, 1. And the coordinates of this point over here is negative 1, 1, right? Notice the y values are the same, but your x values are opposites, okay? Let's go to another point. I have this point right here and this point right here. What is the coordinate of that first point right here? That's what, 2, 2? What are the coordinates of this point over here? Negative 2, 2. Notice again, y coordinates are the same, and the x's are exact opposites. You can do that with any of these points on this graph, and you'll find that that's true. And of course, the reason the y values are the same is because these points are at the same height from the x-axis, so the y values are the same. They are equidistant from the y-axis, one going right, one going left. So the absolute value of that x-coordinate will be the same. The distance from the y-axis will be the same, but they will have opposite signs. Now, we're putting this together then in terms of how we can test for symmetry. So let's look at these tests. If the equation is unchanged when y is replaced with negative y, there is symmetry to the x-axis. Okay? Now, let's go through that again. If we're testing for symmetry to the x-axis, we're changing y to negative y. You'll notice it says nothing about changing x. We're only changing y. Okay? So, basically, in terms of points, what this is saying is that if I have an x-coordinate with a certain y-coordinate, I will have the same x-coordinate, but the y will change its sign to negative y. These points will both be on the graph. Okay? The second one says, if the equation is unchanged when x is replaced with negative x, there is symmetry to the y-axis. Okay? That's what we just saw a minute ago in this picture. Notice the x is replaced with negative x, but the y values stay the same. So here we're saying if I have x, y on the graph, I will have negative x, y. Notice the y value stays the same. And then finally, if the equation is unchanged when both x and y are replaced with negatives, and that means at the same time, okay, there is symmetry to the origin. Now, let's look at that in terms of ordered pairs. Here we changed y to negative y. Here we changed x to negative x. Notice here we're saying we have x, y. We're replacing both. Okay, so if this point is on the graph, the opposite of x and the opposite of y, that point is also on the graph. Now, what we're going to do first is some practice with graphing in terms of symmetry, and then we're going to go to equations where we test for symmetry by working with the equation. Okay, so let's remember what we did here. This says to complete the graph using symmetry to the x-axis. Now let me review right here. When we're talking about x-axis symmetry, what are we doing? We're changing y to negative y. Okay, so how are we going to complete this graph? Well, let's look at this. This point right here has coordinates 0, 2. If we're changing y to negative y, then the point 0, negative 2 would also have to be on that graph. So I'm going to put a point right here. Okay? It looks like the graph also goes through 1, 1. If I'm changing y to negative y, then that would be 1, negative 1, wouldn't it? Okay? Now, it looks like from this picture, you'll see up here at y equals 3, it looks like I'm sort of approaching that like an asymptote. So what I'm going to do is go down here to negative 3 and kind of get that same sort of picture here. And I'm going to sketch in these points. And notice if I've got symmetry to the x-axis, then the x-axis needs to be what's dividing these two. They should look alike. I should be able to fold my paper on the x-axis and have these two being the same. So I have a mirror image where the mirror would be the x-axis. Okay? All right, this one says to complete the graph using symmetry to the y-axis. Again, symmetry to the y-axis, we're changing x to negative x. Okay? So we're going to do the same sort of thing. Here's that point 1, 1. Now, if I change x to negative x, I have negative 1, 1, don't I? Okay, negative 1, 1 would be right here. Okay. It looks like the point 0, 2 again. So if I change what? Well, I can't change the x because negative 0 is still 0. Notice we're changing x, not y. 0, 2. That's that same point right there. What is the coordinate of this point? The coordinate right there is what? 2, 0. Now if I change the x to negative, that's negative 2, 0. Okay? Now actually what's happening is my graph is coming up and doing this. It's going in the opposite direction. Okay? Now again, picture if you fold your paper on the y-axis, are you getting those two coinciding? Do you have a mirror right here on the y-axis where you've got a reflection? You do, don't you? Okay? So that's the thing you want to think about when you're doing symmetry to the y-axis. Okay? All right, finally we have a graph, and it says to complete this graph using symmetry to the origin. Well, our rule for origin symmetry, we change both x and y to opposites. Okay? So let's see about doing that. It looks like the point 1, 1. If I change both, I have negative 1, negative 1, don't I? Negative 1, negative 1. Okay? Let's see, 1, 2, 3, 2. Looks like the point 3, 2 right here. So if I change them both, negative 3, negative 2. Negative 3, negative 2. Okay? Let's see, this is 1, 2, 3, 4. 1, 2, 3. If I go negative 4, it's going to be going down. Actually, what happens here, if I can sort of sketch this in, is your graph does something like this. Now, origin symmetry is a little bit harder to picture because you can't think about folding on the origin particularly. But what you want to think about here is that it's just sort of reversed, both of them changing signs. And so you've got here, if you could sort of turn that over and twist it, then you would have this side down here. But the idea of completing symmetry to the origin is to find points here, change the sign of both x and y, and that will give you corresponding points for the other graph. Now, having looked at these graphs, let's look at simply equations. Okay? We're still testing for symmetry. We're not going to do this on a graph. We just want to know, does this equation have symmetry? Well, let's start. If I'm checking for x-axis symmetry, what do? I change y to negative y. Okay? So let's do that in this equation. 2x squared minus 3, I'm changing y to negative y, equals 12. So when I simplify this, negative 3 times negative y is a plus 3y equals 12. Now look at this equation and compare it to the original. Are they the same? They're not, are they? Because this sign is opposite. These are not the same. If these are not the same, then there is no symmetry to that x-axis. Okay? Now, for y-axis symmetry, what do? We change x to negative x. Okay, so let's do that. I have 2 times, changing that x to negative x, got a square, minus 3 times y equals 12. Now remember, you square first. If I square negative x, I get positive x squared times 2. So that's 2x squared minus 3y equals 12. Does this equation look just like the original? It's exactly like it, isn't it? It's the same equation. And remember, in your rule, it said what? If the equation is unchanged. Okay, my equation is unchanged, so I do have symmetry to that y-axis. Okay? Now, let's test for origin symmetry. Remember, for origin symmetry, you change both. Okay, so I'm going to have 2 times negative x that I square minus 3 times negative y equals 12. Again, you square first and get positive x squared times 2 is 2x squared. This is going to be a plus 3y equals 12. Is this the same? No. It's not the same, so there is no symmetry to the origin. So the only symmetry that this graph would have would be to that y-axis. So that gives us a mental idea of whatever happens sort of on the right-hand side of that y-axis, the same sort of picture, mirror image is going to happen on the left-hand side of that y-axis. Okay, let's test this equation for symmetry. Let's start with x-axis. Remember, we're going to change, I guess I can't spell there, x-axis, we're going to change y to negative y. Okay, 4x squared minus 9 times negative y, I'm going to square that, equals 36. If I square first, I get positive y squared times a negative 9. That's a negative 9y squared equals 36. Is that the same? It's exactly the same, isn't it? So, yes, I do have symmetry to the x-axis. Okay? What about y-axis? What do? Change x to negative x. 4 times negative x that you're going to square minus 9y squared equals 36. Do you see what's going to happen, of course? Squaring that, we get positive x squared. 4x squared minus 9y squared equals 36. Do we have symmetry? Yes, we do have symmetry. Okay, one more. Check for origin. Now we're going to change them both. Minus x squared minus 9 times a minus y squared equals 36. Squaring first, I get 4x squared minus 9y squared equals 36. Same equation still. Yes, I have symmetry to the origin. This equation has symmetry for all three, x-axis, y-axis, and origin. Now, you'll learn more about equations like that a little bit later in your college algebra course, but that still gives you an idea of what to look for. And when you get through graphing your equation, if it doesn't exhibit this symmetry, then you know you've done something wrong. Okay? Now, I hope you've noticed that one quick, easy thing to do here is to notice that if your variable is squared and it doesn't appear anywhere else, then you're going to have some symmetry. If the x is squared, you're going to have symmetry to the y-axis. If your y is squared, you're going to have symmetry to the x-axis. Now notice that's if there's no other x or y value in there. Okay? Now, we're going to go back to graphing, but I want you to notice the instructions here. Graph the following equation using intercepts and symmetry. Okay? Now, let's find intercepts first. Okay? And I'm going to do this as an ordered pair. I'm going to let x be 0 to find the y-intercept, right? Well, that's real easy. If x is 0, what do we get for y? We get 0, don't we? Okay? Now, finding this other one's going to be a little bit hard. If we let y be 0, I have 0 equals x cubed minus 16x. Now, what do I need to do with that? Since I have a 0, let's factor. 0 equals x times x squared minus 16, factoring out that common factor of x. And then we can factor x squared minus 16, can't we? 0 equals x times x plus 4 times x minus 4. Now, if I set each of these factors equal to 0, x is 0. X plus 4 equals 0 gives me x equals negative 4. And x minus 4 equals 0 gives me x equals plus 4. So if x is 0, y is 0, we've already listed that point. If x is negative 4, y is 0. And if x is positive 4, y is 0. Okay, so I have 3 intercepts. Let's go ahead and locate those intercepts. I have 0, 0, 1, 2, 3, negative 4, 0, and 1, 2, 3, 4, 0. Okay, so I have those 3 points. Now, I know that these are the only places that my graph will touch or cross either of these axes. Okay, so I know not to do cross any other place besides these points. Now, let's see about symmetry. If x is changed to negative x, let's do that first. Negative x, I'm going to cube minus 16 times negative x. Let's see what happens. When I cube a negative, I get a negative, minus x cubed. A minus times a minus is a plus 16x. Does this look like the original? No. Okay, so changing x to negative x, there is no symmetry to the y-axis. Okay? Or what about if I change y to negative y? Negative y equals x cubed minus 16x. Now, even if I multiply through by a negative 1, are these equations the same? No, they're not. So there is no symmetry to the x-axis. What about the origin? I'm going to change both of them. Now, I've already seen if I change x to negative x, I get negative x cubed plus 16x over here. And of course, if I change y to negative y, I have a negative y over here. Look what happens now when you multiply through by a negative. Y equals x cubed minus 16x. Is this equation the same as this one? Yes, it is. We have symmetry to the origin. Okay? Now, what that tells me then is if I just graph, say, for positive values of x, if we have symmetry to the origin, remember all we do is we change the sign of both the x and the y. So here's what I'm going to do. I already know what happens when x is 0. Let's get a value for x equals 1. Okay? Well, 1 cubed is 1. And if I put a 1 here, I have a minus 16. I get 1 negative 15, don't I? Okay? Now, I'm not going to have really enough space, so I'm going to come way down here, 1 negative 15. But what do I also know? If x is negative 1, y is positive 15. So for negative 1, I'm going to be way up here somewhere, right? Okay? Now, if x is 2, okay, 2 cubed is 8, minus 2 times 16 is 32. Okay, let's see. That's a negative, what, 24? Okay, that's going to be even farther down. Let me come down here. I also know negative 2 gives me positive 24. Way up here somewhere. Okay? Let's do 3 for x. If x is 3, 3 cubed is 27. That's a 48. And let's see, that's a 21, negative 21. Okay, so we've come back up a little bit, haven't we, when x is that. So between that negative 15 and negative 24. And I also know if x is negative 3, I get a positive 21. Negative 3, that's going to be not quite up as far. Now, that sort of looks really wild. I don't know if you can see all these points or not. Let me darken those a little bit. The key here, if you're not careful, that just kind of looks like a jumbled up mess, doesn't it? But what I want to do is do this in succession. I'm going to start with x equals 0 and move to x equals 1, and I'm down here. So I'm going to go from this point down to this point. And then whenever x is 2, I'm at this point. When x is 3, I'm here. When x is 4, I'm up here. Now, what happens here? I might do one more value, like let x be 5. 5 cubed is 125. And 5 times 16, let's see, that's 80. Notice I'm getting a positive answer. So that tells me when x is 5, I'm getting a positive answer. My graph is going to go ahead and go up here, and it's going to keep going up. Now, I'm going to do from 0 going this way. Negative 1, I'm there. So I'm going to connect these points. And then negative 2, I'm here. Negative 3, I'm here. Negative 4, I'm here. And what do I know? Since I got a positive answer for positive 5, if x is negative 5, I'm going to get a negative answer. So the graph is going to keep coming down like this. Okay? Now, we got some really big numbers here, so it's hard to make a real accurate graph. But do you get the idea of how that symmetry helped us a little bit? Because I only had to plug in positive values, and then I could just change my signs, and I knew another point on the graph. So that symmetry really did help out a lot. It also helped knowing that these were the only places that I could cross my axes. That tells me not to look for this graph to turn around and come back down, because I would have to have another intercept if it did that. So I know the graph is going to just keep going up. Okay, we have one other problem to do here. Graph the following equation using intercepts and symmetry. Okay, so let's see. If x is 0, If x is a 0 here, I have 0 equals y plus 2. Can you do that in your head? Y equals negative 2 then, doesn't it? Okay. And if y is 0, it says x squared is 2. So x would be what? Plus or minus the square root of 2 whenever x is, y is 0. X squared equals 2, so x would be plus or minus square root 2, okay? Which we know is about 1.4. Okay, let's locate our points. 0, negative 2, 1.40, and negative 1.40. Again, we know that's the only places we're going to cross either axis, okay? Now, what about symmetry? Is it obvious that if we change y to negative y, our equation will be different? What about if we change x to negative x? See, that one will be the same because we're squaring it. So, since I can change x to negative x and not affect the equation, I know I have y-axis symmetry. What if you change them both? It would be different, wouldn't it? Because this would stay positive, but that would be negative. See, a lot of times you can do those tests for symmetry pretty quickly. I have y-axis symmetry, so I know that whatever happens over here, the same thing's going to happen over here. Mirror image. Okay, I've got these points. Let's go ahead and get a couple of other values here, and I think I'm going to solve this for y to make it easier. Y is going to equal x squared subtract 2. Okay, so if x is 1, 1 squared is 1, 1 minus 2 is a negative 1, so I have the point 1, negative 1. Let's go ahead and use x equals 2. 2 squared is 4, 4 minus 2 is a 2, so I have the point 2, 2. Okay, and let's do one more. If x is 3, 3 squared is 9, minus 2 is 7. 3, 1, 2, 3, 4, 5, 6, 7. We're right up there. I'm getting a curve up here, and what do I know? Mirror image over here. So let's just go straight across these points, and then we can connect, and you can see your symmetry. Okay? I hope that you're seeing how using intercepts and symmetry can speed up that process a little bit in terms of finding the graph of an equation. Now, you're still doing a lot of point plotting here, and as I've said before, as you get on into your study of college algebra, you're going to find out more about these equations, and all of the things that you learn will help you to streamline your process and do these graphs much quicker. I hope that this lesson has been beneficial for you. Thank you.